Welcome back. Let's do some more examples. For this one, we're creating 6-letter passwords, and for this one, we are making the probably not good choice to only use 26 lowercase letters to work from. So no capital letters, no punctuation marks, no numbers, just the 26 lowercase letters, and that's it. And we'll select one of those passwords at random. And before we do that, we can think about our sample space. Because remember, sample space is just the ways to do this experiment with no restrictions. And if you had no restrictions and you were just filling in the 6 little positions of your password, for the first letter, you'd have 26 choices, and you'd have 26 choices for the second and the third and the fourth and the fifth and the sixth. So really, our sample space should be 26 to the power of 6. Okay, now that we've got our sample space worked out, let's start thinking about the events that we're interested in. So for part A, we're interested in what if we wanted to have a password that has no repeated letters. So let's think about this for a second. If we're counting the number of ways to have no repeated letters, you could do this with the multiplication principle. So you could start filling things in, 26 choices for the first spot, then 25 for the next, and so on. Or if you're being a little bit more clever, you could think about how really this is a permutation, because out of the 26 letters that you would have in total, you would have to select 6 of them and then put them in some sort of an order. And that's quite literally P266. That's the number of ways to select 6 different letters, so nothing's repeated, and put into some sort of an order. So that means probability of us getting no repeated letters should be the permutation of 26/6 over 26 to the power of 6, which is about just almost 54%, so 0.5366. I'm going to round all of these off to 4 decimal places when I do my computing. Okay, starts with a vowel for part B. So for this one, again, if we're thinking about the number of ways to start with a vowel, and again, reminder from chapter 3, when we're doing a part B and a part C, the restrictions don't roll over. So in part A, it was that nothing was repeated. For part B, maybe things are repeated there. The restriction from part A doesn't also hold over for part B as well. So when I say starts with a vowel, could start with a vowel, and maybe there might be repeated consonants or repeated vowels or anything. Sky's the limit. The only restriction for B is that the first character must be a vowel. And for that, I'm just going to think about multiplication principle. For the first position, you'd have 5 choices, A, E, I, or U, A, E, I, O, U. And then for the remaining 5 positions, you could put anything in there, and we don't care if it repeats or not, or if it's a vowel or not. So for the other 5 positions, there would be 26 choices for each of them. So for the second, third, fourth, fifth, and sixth, there should be 26 options, or basically 5 times 26 to the power of 5. That's the number of ways to start with a vowel. And so the probability that we start with a vowel should just be 5 times 26 to the 5, all over 26 to the 6. And that's about 19-ish percent, 0.1923. Okay, let's continue with part C and D next. We want our password to have the letter Q in it, and we want it to be there twice in some place. So we need to know how many ways are there for us to have exactly 2 Qs. So if I'm thinking about my 5, 6, there we go, 1, 2, 3, 4, 5, 6, my 6 positions, if I wanted to count how many ways are there to fill those in with a 2, with a Q rather, I would say, well, I need 2 of these positions to be Qs. So my first task is, out of the 6 positions, decide on 2 of them to contain the letter Q. So I might decide that a Q is going to go here and also here. So I really only have one choice. Once I've decided where the Qs go, there we go, there they are. That would leave me with 4 places left, and for those 4 places I could put whatever. The only thing that I couldn't put in those 4 places would be a letter Q, because that would give me more Qs than I need. So I've already decided on 2 out of the 6 places to have the letter Q in them, and then for the remaining 4 places, I just fill them in with whatever. It doesn't really matter. Any one of the other 25 letters for each of those 4 places. So 25 for the first blank spot, 25 choices for the next, and 25 for the next, and 25 for the next. Or basically 6C2 times 25 to the power of 4. Okay, so that means that the probability of us getting 2 letter Qs in our password, if we just select a password at random, should be 6C2 times 25 to the 4 all over 26 to the 6. And that's 0.01897. Okay, if I round that off to 4 decimal places, it rounds off to 0.0190. So almost 2% chance that you'll have 2 Qs in your password. Okay, last one. Lots of restrictions here. We want 4 different vowels, we want 4 different consonants, and not just that, we want the vowels to be kept separated from each other. So if I'm thinking about this, there's actually a bunch of tasks that I'm going to need to do, because if I'm thinking about, for this event, 2 vowels, 4 different consonants, vowels kept separate from each other, the first thing I would have to know is which vowels am I using and which consonants am I using. So out of the 5 vowels, I would need to select 2 of them, so 5C2. And out of the out of the 21 consonants, I would need to select 4 of them, 21C4. So in this point in your life, you would know you're using an A and an E and a P and a Q and an R and a Z. There we go. You know your 6 letters now. What you don't know is what order they're going to go in. So now we need to remind ourselves, how do we arrange things and keep things kept separate? The vowels are the things that are being kept separate, so we ignore the vowels for now, and we are going to first arrange the 4 consonants and say, well, you've got 4 things, so 4 factorial ways to arrange the consonants. Then we would have to decide on where the vowels are going to go. Am I going to put a vowel at the beginning, between the first 2 consonants, between the next 2, between the next 2, maybe put a vowel at the end? I have 1, 2, 3, 4, 5 places where I could stick in a vowel, and I need 2 of them because I have 2 vowels to place in there. So out of those 5 potential spaces for vowels, I need to select 2 of them. And then once I know that, let's say, a vowel is going to go here and a vowel is going to go there, I need to decide what order to place those vowels in, which is, since it's 2 things, 2 factorial ways. So this is the number of ways for me to carry out my event. I have to choose who are the vowels, who are the consonants, arrange the consonants, find spaces for the vowels, and then once I found spaces for the vowels, arrange the vowels. So this should be the total number of ways to do my event, divided by the number of ways to carry out the experiment, 26 to the 6. And that gives me a probability of about 9-ish%, not quite 10, 0.092996, or rounding it off to 4 decimal places, 0.0930. So just a little bit above 9%. Okay, let's do another one. This time we've got a lacrosse team, and on this lacrosse team there's 10 players. Blanche, Dorothy, and Rose are 3 out of the 10 players. We are going to line these players up randomly for a photograph, and we want to know what are the chances that Blanche, Dorothy, and Rose are all standing next to each other. So first off, our sample space. That's just us carrying out this experiment. That's taking 10 players and arranging them in a random order. That's 10 factorial ways for us to do that. So quick and easy sample space to count here, 10 factorial. For our event, E is our event that the three friends are standing together. And so if I'm thinking about counting the number of ways that E can happen, I need to remember, well, how do I arrange things where things are being kept together? I've got Blanche, Dorothy, and I've got Rose, and then I've got 7 other players. Player 1, 2, 3, 4, 5, 6, and 7. Remember, to keep things together, we used a box. If I want Blanche, Dorothy, and Rose to all be standing next to each other, I'm going to first put Blanche, Dorothy, and Rose into a box, and then that way when I move them, I'll be moving the box, so all 3 friends will move simultaneously to their new location. So first task is arrange the individual items and also the box. I have 8 things in total, 7 separate individual players plus 1 box that contains our 3 friends. So I've arranged our 7 players plus our friends. That's 8 factorial ways to do that. So now I know that the 3 friends are together somewhere. What I need to also know is what order are the 3 friends in inside the box. Remember, that's the second step. We arrange individual items and the box. Then next we arrange inside the box. And since there's 3 friends inside the box, there's 3 factorial ways to arrange them. So, probability of E happening, probability of our 3 friends all being standing next to each other, should be the number of ways for E to happen. 8 factorial times 3 factorial, all over the number of ways that our experiment can happen, which is 10 factorial. And then we just need to compute this and find out that our probability for Blanche, Dorothy, and Rose to be standing next to each other is around a little bit above 6%, 0.0667. Okay, let's do one last. Here I've got a class where there's 45 people in it, and in this class of 45 people, 7 are wearing hats. Just as a little aside there, of course, if there's 45 people and there's 7 wearing hats, that means that the other 38 have no hats on their head. Okay, so that's our first part. We've got really our 45 people broken down into 2 groups. There's 38 without hats, 7 with hats. I'm going to select 5 people at random, and I'm going to take those 5 people to the cafeteria for us to all go buy some snacks. First off, if I'm thinking about the sample space, this is just me selecting 5 people out of the class. The order that I select them doesn't matter. They're not each doing a special job. They don't have a special role to complete. It doesn't really matter who's the first and who's the 5th person. So for my sample space, it's just a combination. Out of the 45 people, I just need to select 5 of them. Okay, we want for part A the probability of exactly 2 people wearing hats. So the number of ways to get exactly 2 hat wearers would be really 2 tasks. Number 1, out of the 7 people wearing hats, you would need 2 of those people. And then that means that out of the other people, the 38 who aren't wearing hats, you would need 3 of them because you have to make a group of 5. So the probability of us getting 2 people wearing hats should be 7C2 times 38C3. That's to select 2 people with hats and 3 people without, out of 45C5, out of us just selecting any old 5 people from our group of 45. And that gives us a probability of about 14.5% thereabouts, once I round it off to 4 decimal places, 0.1450. Okay, so now that we know the chance of us getting 2 people in the little group wearing hats, we might want to know the question of what's the probability of getting at least one person wearing a hat. So what's the probability of us getting one hat or more? We could do this directly, but again, that's going to be a lot of scenarios because you'd have to find the probability of getting one person wearing a hat, or two, or three, or four, or five. And that's 5 different scenarios, and I do not feel like doing all that work. So this is where we say, okay, we should maybe think about using the complement instead, because instead of us finding 1 or 2 or 3 or 4 or 5 hats, what if we did the opposite? What if we did 1 minus not getting 1 or more hats? And if we didn't have 1 or more hats, that would be us having no hats. So everybody is not wearing hats. In other words, we're looking really for 1 minus the probability of 5 people wearing hats. Or 5 people not wearing hats, rather. And that's easy enough to compute, because for 5 people to not be wearing hats, that means I would select my 5 people out of the 38 who don't wear hats. So for 5 people to not wear hats, that would be 38C5 out of the 45C5 ways there are for me to select just 5 people in general. And that turns out to be actually a pretty good probability, 0.5892. So if I were to select 5 people at random from that group of 45, if there were 7 people with hats on, then the chance of me getting 1 or more people in my group of 5 having hats is almost 59%.